Today we'll talk about just kind of some basics of GPS, how it works, and kind of the fundamentals behind it. And then from there, we'll get into the actual GPS surveying that we do. So you can think of GPS as kind of a spectrum of accuracies, levels of technology that build off of one another. Today we're going to introduce the theory and physics behind GPS. We'll understand the sources of error, and there's a lot of effort that goes into correcting that error so we can get more accurate location information. And we'll explore how we do GPS measurement. There's different systems for GPS measurement, and we have associated accuracies with them, right? So you've got the GPS in your phone or your car. You've got the GPS maybe that an airplane has. And then you've got the GPS for RTK surveying. So there's layers of technology and accuracy that improves the accuracy as you go. So the basics of how it works, right? We have satellites. When the first system was launched, I think there were like a dozen satellites or something. There's scores of satellites now with different countries that run them. So you've got the US system, you've got the Russia system, you've got Korea, Taiwan, China, or sorry, Japan, China. They all have their own systems. And the nice thing about it is that we work together so that they can all work together. So meaning like we can have Russia satellites that are going around the planet, just as we have Chinese satellites and US satellites, and they all are sending the same kinds of signals and our receivers can use them. So we're all benefiting from it, which is nice. Granted, the satellites were launched, GPS systems were launched so that we could have intercontinental nuclear missiles. And we could guide them to, destroy each other's cities and navigate submarines and jets and all that stuff. So it was a military application originally, and since then, civil society has embraced it and it's become integral to how we operate and run and work. So the basics of GPS technology, we have atomic clocks on board, and actually GPS satellites have anywhere to up to 4 or more atomic clocks. And these clocks are highly accurate, right? They're measuring the rotation or vibration of decay. I don't actually know. I think it's decay of atoms, and there's a very steady rate to that. And then you can, say anytime we have, 92,000 whatever protons coming or neutrons coming off of this atom, that's a second, right? So that's how atomic clocks work. They calibrate a second based off of some atomic process. We know the speed of light. This is a constant thing, and the speed of light is how fast radio waves transmit between satellites and our planet. So any electromagnetic wave or particle travels at the speed of light, visible light as well as radio waves, microwaves. And then we have the theory of relativity from Einstein. So there's a lot of big stuff happening that influences how GPS works. It's pretty wild physics. So you've got these satellites in space, they're transmitting a time signal, and that signal spreading out in a sphere away from the satellite towards our planet. And so wherever we are on the planet, these are satellites, they're sending out that signal, it's radiating outwards with a timestamp on it. Where we are and we're receiving the signals is where all these spheres are intersecting. I'm showing 3 right now. 3 will give you an X and Y. 4 will give you X, Y, Z. And so that's the visualization of those signals that are sent down to our planet. Do I have a video here? Yes. System.
At over 20,000 kilometers above sea level is a constellation of satellites, each orbiting Earth every 11 hours and 58 minutes. These satellites are continuously beaming data down to us on Earth, which is in turn received by devices such as your phone or navigational units in your cars, allowing you to see where you are on the planet. There are a lot of misconceptions about how GPSs actually work, an example being that your phone and the GPS satellites are both talking to each other. So let's get down to it. How do GPSs work? GPS stands for Global Positioning System, which works through trilateration. An over-twin equivalent system is nav-multilateration, which is commonly misconceived. There are many different types of navigational satellite systems from countries across the world, but the most popular and commonly used system is Navstar, which is the USA system. There are, however, Russian, Indian, Chinese, and European equivalent systems, although the Indian and Chinese systems sit in a geosynchronous orbit above their countries, which means they are not worldwide systems. The Navstar system, which is simply referred to as GPS, is what we'll be focusing more on, although most phones and devices tend to have the capabilities to use both GPS and GLONASS. GPS satellites are set up in such a way that from almost anywhere on the surface of Earth, you should have a direct line of sight of at least 4 GPS satellites. This is quite important on the basis that GPS point positioning requires at least 4 satellites to calculate 3 position coordinates and the clock deviation. As GPS units are receivers, there needs to be something sending some sort of signal to devices such as your phone to receive. Each GPS satellite broadcasts a navigational message towards Earth, which contains an extremely accurate timestamp, which is obtained through an atomic clock which is on board with these satellites. And the satellites also broadcast their position at the time of broadcast, with all GPS signals broadcasting at 1.5752 GHz and 1.2276 GHz. These 2 bits of information allow you to work out your position on Earth. With these satellites all sending exceptionally accurate time down to Earth, your phone or GPS receiver can compare the difference of time between when the signal was sent to when it was received to work out the distance between you and the satellite. By multiplying this time difference with the speed of light, as the signal is sent at the speed of light, you can begin to get the distance away you are from that satellite. As these satellites are also sending whereabouts they are, you can begin to draw spheres around the satellites, with you being somewhere on the outer border of that sphere. As we introduce more GPS satellites into the mix, we begin to get closer to where we are. By calculating the time differences between these satellites, we move from having no idea where we are to being able to pinpoint where we are, typically down to 5 to 10 meters on average, with the potential error being around 15 meters. There are a lot of factors which escalate the potential error, but the most significant is due to the ionosphere, a part of the upper atmosphere extending from 60 kilometers to 2,000 kilometers, where free electrons occur frequently enough to have an appreciable influence on the proportion of electromagnetic waves passing through this layer. This error is substantially smaller when satellites are directly overhead, compared to being larger the closer the satellites are to the horizon relative to you, as the path between you and the GPS satellites goes through more of the atmosphere compared to being directly overhead. Even things such as small variations in the atomic clocks found on board these satellites can cause major errors. A clock error of 1 nanosecond can translate to a 1 foot or 30 centimeter miscalculation of satellites.
I was trying to do pause. I love that right there. Just these tiny little delays in the signal, right? From bouncing, we talked about, I don't know if he'll talk about it in this video, but multipath error, bouncing off a building or something like that, getting delayed and slowed down in the ionosphere. All the other errors that we'll talk about in a second can translate, just teeny tiny little delays in the signal can translate to errors, and those all kind of add up, right?
Can translate to a 1 foot or 30 centimeter miscalculation. Then the theory of relativity kicks in, with the atomic clocks ticking ever so slightly slower than clocks which are stationary on the ground, which translates into a 7 microsecond a day delay. General relativity then also kicks in, with the effect of the gravitational frequency shift being far greater than the 7 microsecond per day delay due to the velocity relative to Earth. As the theory states that a clock which is closer to a massive object will be slower than a clock further away, the atomic clocks on board the GPSs are faster by about 45.9 microseconds per day. Combining the 7 microsecond a day delay due to the satellite's velocity relative to Earth and the GPSs being further away from Earth, this adds up to a 38 microsecond delay, which if left uncorrected would translate through to a 10 kilometer a day pseudo-rounded error, rendering GPSs invalid from the get-go if this was not to be taken into consideration.
So if we didn't have the theory of relativity, which states that time actually travels or passes more slowly the closer you are to a massive object, or as well as your speed, right? If you're traveling more fast, time is slower for you. If they didn't account for the relativity, GPS wouldn't work. That blows my mind. I just wanted to share that.
This is compensated by the GPS's clock's frequencies being slightly slowed down from 10.23 megahertz to 10.22999999,543 megahertz to cancel out the effects of relativity. So next time you turn on your GPS on your phone or other device, you should now realize just how much physics and maths is going in towards you finding your own location. Thank you for watching. Be sure to subscribe.
Any thoughts on that? Should have posted that video. I'll post that on Canvas. Yeah, it's pretty wild. And here decimal points matter, right? Decimal places matter. I spent a lot of time harping on people including too many decimal points in civil engineering because our models and measurements are never that accurate, but here it obviously matters. So let's talk about GPS accuracy versus precision. And this is an important concept. We can have very precise points, meaning we know so you think of precision as error. How much spread in your measurement do you have? So highly precise, but poorly accurate. It's got you in the wrong place, right? Here's high accuracy, high precision. We have relatively high accuracy because that error bubble is pretty much centered around where we actually want, but we have a pretty big error bubble. And then this is low accuracy, low precision. So accuracy is how close you are to predicting the correct location. Precision is how much your error is around that. So here's just a schematic of different types of GPS accuracy. So here's the true position. You've got prior to 2000, May 2000, we had what was called selective accuracy, and this was the system in place by the US government that basically scrambled the GPS signal and made it less accurate for civilian uses. Military, they had the software, the algorithm to de-scramble that signal and get the higher accuracy 15-meter. But prior to 2000, when you had if you had a GPS receiver, you were plus or minus 100 meters. So would that work for a car navigation system? Yeah, because 100 meters, 300 feet, that's a football field. So you could be on this road or that road, right? So it wouldn't work. Fortunately, based on negotiations or whatever, they realized the civilian applications were becoming so important that they turned the system off. And we'll see a graph of what that looks like. WAAS, I don't know the name of that acronym off the top of my head right now, but this is called Differential GPS. And we'll talk about what that is, but basically the idea is you're talking to, you have special radio equipment in your GPS that can talk to a control point, a highly accurately known position, which is also talking to the satellite. So you get a correction basically from that known position based on what you're hearing from the satellites and what it's hearing from the satellites. So the video and your reading talked about GPS error. I'll just go over it briefly here. One of the main ones that we'll run into with RTK is when you're surveying against large objects that can reflect the signal. This could be a building, water, trees, anything that can reflect radio signals, water being the biggest one. When you're in a forest with trees, GPS is not working very well. That's why when I'm ever doing surveys on a river or something like that, I'm trying to do that during the fall or winter when the leaves are off. Or maybe there's no trees. If you work out here in the desert, you're not running into trees very much. This error can be up to 1 meter. And again, it's just basically the signals bouncing off of something. So instead of you receiving a GPS signal on your tractor, if you're doing harvesting crops and highly accurate, precise harvesting, you're getting this bounce. And so there's a bit of an extra delay that happens in that time signal, making it seem like you're actually farther away than you would be from that satellite. So you're getting the direct signal or you're getting the bounce signal. So here's just an example of things that can cause multipath error. Here's the direct reception of the signal from the GPS, and here's bouncing off of power line cables trees, water, buildings, and all these things can cause that error. Yeah, I was getting took a GPS course with a professional who was talking about they were out surveying railroad tracks, and anytime the train would go by, there's this relay system of radios, and so when the train's coming by, it's sending out really intense radio communication down the train line, and that would scramble and completely mess up their survey. So radio interference can be a problem as well. So you guys have probably heard of the term refraction. Refraction is where any electromagnetic wave, when it encounters a different medium, be it your space, we have the atmosphere, or water. We know it from water, basically, if you're looking at a fish or something in the water, light is actually bent. Light slows down in water. And because of that, it takes a different trajectory. And so that means that what we see in the water is actually a little bit shifted from what it actually is. So if you go to grab that fish, you're not going to actually be grabbing the fish, you're just going to be grabbing water. So refraction happens in our atmosphere as well, because it's encountering a different density, different atoms. And that bends the light and can increase or introduce a very big error, so up to 5 meters of error. And that can be accounted for by various models, so we can kind of model that refraction. But we also have the problem of, I guess we'll talk about, I think we talked about ionosphere, but that refraction can be a function of the weather of the sun. So the sun sending out electromagnetic waves, which can kind of scramble that signal differently depending on how much energy is coming from the sun. So, because you think about a sunset, the sun turns a different color. When it's lower in the sky, it's traveling through more atmosphere. That's why you see orange and pink light versus when it's above, there's less atmosphere, it's blue or white. The same for satellite signals. So if you get very low satellites, this is called an azimuth angle. Azimuth. When your azimuth angle is very low in the sky, you're getting the signals traveling through more atmosphere, and so it's more erroneous. It's got a higher error with that. And so you can actually have a mask and say, okay, I don't want to get any signals from satellites that are less than 10 degrees from the horizon. So I'm just going to ignore all those satellites because I don't want their signal. Those are going to be really highly erroneous signals. That's called an azimuthal or azimuth mask. And it's just ignoring these low satellites in the sky. All right, so the reading talked about dilution of precision. And this is related to the geometry of the satellite constellation. So the constellation of satellites in the sky, just like the constellation of your stars. And if you've got a real big cluster of satellites, you're not going to get a really accurate position because those spheres are kind of overlapping each other, as opposed to satellites that are spread out. Then you're going to get kind of a better intersection of those spheres of signal. You can have horizontal dilution of precision, vertical, positional, which is just the 3-dimensional, and then time. These are all impacted by your satellite geometry. Okay, so the dilution of precision, this is kind of a term that you'll see when we get the GPS equipment out. It'll say poor PDOT, poor precisions, something like that if you're getting a bad signal. So PDOT is your position dilution of precision, and it's the aggregate error, so the square root of your horizontal and your vertical precisions squared. You could also think of, let's see which one is G. And so this value is kind of a relative number, and you want to be very low with this particular number. So this is, PDOT value of 1 is the highest you can have. 1 to 2 is excellent. And then down below, you start to get measurements that are just not going to be viable. In your GPS unit, when you're doing your surveying, you can actually set it so that it won't collect a point unless your PDOF is a certain low value. It just says, you know what, this is not going to be accurate enough. I'm not going to let you collect a point. You can force it to, but sometimes you go with those rules that you put in the system. So it's actually easy to model what your dilution of precision is going to be based on where satellites are. And so each satellite, we know its trajectory in the sky. You can open up software websites that'll tell you at a given time of day how many satellites you're going to have, what their position in the sky is going to be. And so over time, you can actually plot your dilution of precision and understand when you're going to have good, better or worse windows. Just another example of what can affect it is here we are in, I think this might be Bryce Canyon. So somewhere in a canyon where you have a very limited view of the sky, we're gonna have a lot of situations here in the mountains, if you're really close to a mountain or a canyon wall, where all of a sudden you're losing a third or a quarter of your sky. And that also means you're losing, if you don't have visual sight of satellites, you're not gonna get the radio signal from them. So the more open sky you have, the more opportunity you have for more satellites that are spread out and a better dilution of precision. So this is what a time series looks like for dilution of precision. So the red is geometrical. We have time, position, vertical, horizontal. Geometrical is kind of the addition of everything. So it includes time and position. Position is the inclusion of your vertical and horizontal. So because we know where all the satellites are, and over time, and you know where you're going to be on the Earth, you can then map out your PDOF is going to be, and if it's going to be acceptable for your survey. Just another example of the software. I think this is one we'll use. This is from an app on an iPhone. You can open it up, and it'll tell you what satellites are in the sky, what satellite systems they come from. So here's the US system, GPS, or Navstar, GLONASS, Galileo. I think that's the what this one is. Here's our dilution of precisions, number of satellites. So it's going to change over time because everything's moving, right? And I don't know what it is, but it always seems like right around 2 or 3 o'clock, if you've been surveying all day, everything stops working well. I don't know if that's just something that's happened a few times, and I think that's how it always is. But there's always going to be a time of day where you're going to have less satellites and maybe higher dilutions of precision. So like, oh, what's going on? Okay, so selective availability. Let's talk a little bit more about this. Before May 2000, the US added a time-varying obfuscation code to its GPS. I love this word, obfuscation. Obfuscation just means we're kind of hiding or making something unclear. This added up to 50 meters of error horizontally and 100 meters vertically. So it made it very, I mean, I had a tiny GPS unit for hiking. If you're just out there in the mountains, you want to find where you are, that's probably good enough. But if I'm using it to supplement car navigation or something like that, it's definitely not good enough. So the idea is maybe you had a pretty accurate location based on the actual system, but with this code, your knowledge of where you were was much less accurate. So here's a graph. Someone was monitoring the error. So we had a known point, known location on the planet, and we're getting the GPS signal. So vertical is in red, horizontal is in blue. And this is May 2nd, 2000, when they turned the SA system off. So here we are with plus or minus, hundreds of meters vertical, and then now we're down here below plus or minus 10. So huge difference. And here's the accuracy that we have now. Here's what this looks like in XY plot. So your horizontal error and vertical error, or sorry, this is with the horizontal error with selective availability on. So plus or minus is 80 meters. I think there's a plot in the reading like this. And here's your elevation. Okay, so there's a lot of different surveying techniques or GPS techniques. We've got just your iPhone or your smartphone GPS, and then you've got different surveying ones. So these are all surveying types of GPS. So the first kind is differential, and then as you get more over here, you get better accuracy. You also get more expensive. So a differential GPS system might set you back a few $1,000s. It's got an extra radio built into it that can talk to the network of control stations that we have. So these are ground-based stations. We'll look at an example of one. There's one in a fire department down on Patterson. So there's a network of these in the Grand Valley on the western slope and across the planet. So differential will get you to sub-meter, right? So somewhere in this realm of things. Really good for mapping if you need highly accurate maps. Not good for like topographic surveying. Then we've got kinematic. So real-time kinematic RTK. This is obviously more expensive. The units that we have run, I think for one of the receivers is about $10,000. The computer to talk to it is like $3,000. So it's for the whole setup on the order of $20,000 to $30,000. So a lot more expensive. If you're using it all the time for your company, it's worth it because it's so fast. It's so easy to kind of set up and go. And this gives you centimeter accuracy, so 3 to 4 centimeters, something like that. Then there's static or fast static. This can get you sub-centimeter accuracy, just a centimeter right here. This is where you're not going around collecting points. This is where you set something up. They use this maybe for tracking the movement of continental plates. I think I have a figure based on that. We'll look at it in a little bit. So if you want to track over time the movement of the planets, crust on the planet, which people do, geologists do, then you can kind of set this up, and it's occupying this position for a long period of time, taking lots of measurements, averaging those, and so you can get really highly accurate points if you're in a static situation. Fast static, 45 minutes or longer, or sorry, 8 to 30 minutes for fast static, so that's fast, right? And then static is, I think, more than 2 hours or something like that. So just to look at what differential GPS is, we're correcting. So we've got a GPS signal to our tractor or excavator. So you guys know that some excavating systems use GPS, and so they'll have an antenna on their bucket, and when they go, they know exactly where they are, and when they're scraping and excavating down, they can get down to, centimeter accuracy of how deep they're digging just with their bucket. So they don't need someone out there with a survey rod. You see people out here with the laser levels, and so they're excavating. That works for a small site. If you've got a big site and you're doing a ton of excavation, like for a highway or something like that, you've got GPS on your bucket and you're measuring that as you go.
They have long blades as well to control the slope at which they grade the ground for.
Yeah, it's awesome. So they're probably using real-time kinematic, but differential GPS is similar. So you've got your satellite system, get your position from your receiver here, but you're also receiving a signal from a ground-based station. It's a tower somewhere, an antenna somewhere, and it's sending out its position and it's correcting. So it knows what the error is at a given point in time, what the DOP is, that sort of thing. And it's able to send a correction to this receiver. So now you've got a ground-based system and a satellite-based system, and you can get sub-meter accuracy. Often you have to post-process that too. So you could collect all your data, all your GPS points, and then go back and find this ground station and get that correction and post-process it later. So you could do it in the field or you can do it after the fact. Now, real-time kinematic, this is what we're going to be working with. And what's happening here is you have a base station on a tripod over a control point. And that control point is something that's been surveyed in. Maybe you've occupied it for like 8 hours with that base station, or maybe it's an existing control point monumented that exists. So there's a network of monumented control points across the city that you could just set up over some known location. And so you set your base station up over that. It's got a GPS antenna on it. You level your tripod. You did this with total stations, right? And so it's all level. You measure the height up to this antenna. So you know your X, Y, Z now. Now this base station sits over there, and it needs to sit over there for 2 hours for reasonably accurate correction, ideally more than that. And it's receiving information from the satellites, and then it's talking to your rover. It's the same antenna, which is also getting signals from the satellites. So you've got a GPS point from the base station and GPS information from the satellites. And so the space station is giving you a real-time correction to your rover based on its known location. And there's a big old equation that's involved, with matrix algebra and stuff like that. This setup has an antenna, so it's taking the signal from here, and with this antenna setup, which we have, and we'll set it up, it allows you to go for miles. So you can have your base station set up on one side of Grand Junction, and if there's not enough buildings and trees in the way, or it's high enough, then you can be surveying for a really long way. Or maybe you're out there in the country and there's not big obstructions, something like that. So antennas are nice because they can extend your range. You can get maybe 1 kilometer with just the base station by itself, but or 500 meters, but you can get a lot. You can get 5 kilometers, many miles with an antenna. So all these systems are very similar, and they're all working off of the signals from the satellites. It's just that now we have different kinds of corrections happening. The satellite gets used to plus or minus several meters on its own, and then we've got additional technology that we can layer on that will give you corrections and give you a higher accuracy. So the kind of latest and greatest system now is, so you've got the standalone system, which is the equipment we have. You set it up, it's getting the base stations, transmitting out to your rover, and you're going around collecting your points. That's a self-sufficient system. You can set that up anywhere in the world. We have what's called virtual reference networks, VRNs, and these are based off of reference stations that are set up on the ground, so antennas that are set up on the ground. And these guys know exactly where they are on the planet, and they're getting those corrections from the satellites. And so in real time, if you're in one of these networks, you got to be inside that box, right? And you get to have 5 of these around you for it to work. You're talking to this system via a cell phone, so you need like LTE kind of connection, a 4G kind of connection. And you're going to get, so that's talking to this computer here, this controller. And so you're getting the corrections now based off of the cell phone network. And so you could just be out there with this rover by yourself. You don't need a base station. You just have one rover, this computer. You need that cell phone connection. And you get the same accuracy that you would with the previous system that I said. And so we're gonna do that as well. We have a real-time network on the western slope that Mesa County maintains. So here's the network, and it looks like, granted, there's not cell phone signal in all these areas, right? But if you've got cell phone signal anywhere from Dinosaur National Monument up here, Craig, down to Thompson Springs, before you get to Moab, it looks like Moab's included. You got Canyonlands right here. Down to Durango, all the way over to the Rio Grande Valley. So it's a pretty big network, and here's Mesa County. So anywhere in Mesa County that you can get a cell phone signal, you can use this network. You got to register with the website, which I've done. And here's what these antennas look like. They're kind of different antennas everywhere. But they're permanent installations. They're getting that highly accurate position, or they know their position, and then they're sending out those corrections. It's a pretty cool system, and this was built by in partnership with these counties, but it started in Mesa County. So we had a big leader when it came to getting this system in place. And so anytime people are doing construction activities in the city, they can log into this and rock and roll, basically. So 23 stations total. These are National Geodetic Survey core stations. We'll talk about that. I don't know what this is off the top of my head, but these are part of the national system for differential GPS. And then these are the extra stations that are part of the Mesa County system. All right, that is my lecture on GPS. Let's clear the room for a few minutes, take a break, and then we'll talk about the GPS assignment that we'll do. Yeah, let's just clear the room and we'll get it some time to do. Okay, so for the GPS assignment, you're going to do two things. The first thing you'll do is define some terms, right? Based on this presentation, based on the reading, and then you will visit this website. So it's a planning website for GPS. You'll put in a location. You'll put in this Azimuth Mask, so 10 degrees, which is basically 10 degrees from where you are. We're not going to read any satellites. We've got a nice little mask right here called the National Monument. Got another mask called the Foot Cliffs, and then a bigger mask called the Grand Mesa. So you put 10 degrees in, well, you're probably already going to get like whatever that is, 20 degrees from all these topographic features around us. Okay, and then you can add an obstruction. So you could simulate the Foot Cliffs or something like that. It's kind of wonky. It was a pain for me to do this. So give it a try. If you're not successful, don't bang your head too much about it. And then you should get a DOP or a PDOP value at that particular time. And then you can do, I'm asking you to give me some screenshots. So how many satellites do you have? What's your dilution of precision? And I think you can do a time series as well with that, like I showed before. Oh yeah, so it'll give you a plot basically for the next 24 hours. And then you can say, okay, does my PDOT go below a certain value, and when does it do it, and when would I want to try to avoid or make sure that I do my survey. And then the last part of this is you're going to download an app on your smartphone. Does everyone have a smartphone? I want to make sure that I'm not excluding anyone. Okay. And I'm giving you some suggestions on there of different apps. The challenge is finding an app that's going to actually log at like a 1 second interval, the XYZ values. Those are hard to come by. There's a lot of them that don't log it unless you're moving, or it's hard to get the data out. So we're collecting data here. And so I've given you some suggestions. I will double check. I can double check these to kind of make sure they work. And the idea is you'll download one of these and you'll start logging your position. And you just set your phone down, outside, inside, doesn't matter, and wait for 15 minutes. And then stop it, download the data, and we'll see what it looks like. So a GPX file is usually the formats of data that you're collecting. And it's just a special GPS file. It's a text file or ASCII. You can convert it to text at this website. So I give you some options for that. We're going to output it to, we haven't gotten to talk about coordinates yet, but you'll output it to UTM coordinates. That just means you're going to get everything in meters as opposed to like degrees, latitude, and longitude. So it's nice when you have everything in Cartesian coordinates or planar coordinates of what we're doing. Okay, so you'll get a download from this website, and then you can have this data. So you'll have XYZ data, and you'll do some statistics on it. You'll do standard deviation, and then a confidence interval. If you don't remember how to do a confidence interval, I'll give you a little refresher there. I know you guys haven't taken statistics with me, but this will be a quick refresher. And the idea of a confidence interval is, I'll mark it real quick. So you'll have so if we're just looking at X and Y, you're going to have points that are all over, and it's going to be kind of wonky. And maybe you'll have something like this. So you'll have, hopefully, if you do it every second, you do it for 15 minutes, you'll have hundreds of points, right? And ultimately, we're trying to figure out, well, where are we actually, and what's the accuracy of that? So say the real point is here. A confidence interval will tell you, okay, for Y, what is the interval within which we expect to see the true mean value fall 95% of the time. It's a little bit of a convoluted definition, but if we were to take a sample, if we were to do that 15-minute sample and do that 100 times, well, the mean value of our sample should fall within this interval 95% of the time. And so we're trying to get, so for your confidence interval, you're going to have an actual Y value, which will be your mean value of Y, and your mean value of X, and that's going to be plus or minus your confidence interval. And that gives you this assessment of how precise the measurement is. This is kind of like an estimate of error. You can do that in Excel. You can do that in R if you're taking a stats class. A pretty quick calculation. And then you can just tell me, well, how accurate is GPS on your phone? And what happens to it over time? Sometimes you'll get in a real wild hair and your position will kind of jump 10 meters or something like that. It's kind of weird. So that'll be due, probably make that due end of next week. All right, any thoughts or questions? We will, for Monday, let me just double check here.
The end of next week, is that like Wednesday?
Friday, yeah. I'll post it today, but yeah, I'll make it due Friday. So let's see here, we got trying to figure out when we're going to go out in the field. Okay, so we'll do a lecture on Monday. Maybe we'll do a basic setting up the stands leveling, kind of like a basic technique for that. And then Wednesday we'll go all the equipment next week and do it on. Yeah, that'll be fun.
Will we just still meet here?
Yeah, we'll put on a meeting here just for the lecture, and then we'll take a break and